Hello and welcome again to my Physics Online Video Lecture Supplement series. In today's video, I'm going to be continuing my lecture set on inductance and AC circuits by looking at AC circuits. So far in this course, we have mostly been considering DC current, although there have been one part of one lecture in which I actually discussed AC current directly, and I've kind of alluded to it elsewhere in these lecture parts, for example, in talking about how a generator works. Today's part of this lecture is to focus more or less entirely on AC circuits, and we'll also be considering what happens when we place things other than a resistor into an AC circuit. So what happens to inductors and what happens to capacitors when they're placed into an AC circuit. Recall that in a DC circuit, the current flows in a single direction around the circuit. For example, this red line would represent the standard DC signal. This could represent either voltage or current. And it's true, though, that this blue pulsating line also would represent a sort of DC signal. And in fact, if you look back on my lecture discussing how a generator works, you can see that even the DC generator has a sort of pulsating signal, pulsating voltage signal. This is the single loop DC generator. This is the signal for many loops, and the more loops that you have, the smoother the signal gets, but there's still a little bit of fluctuation or pulsation for any number of loops shy of infinite. On the other hand, we have also alternating currents, and both this variable current and this green line would represent sorts of alternating currents. Alternating current just means that the current reverses direction within the circuit, and so does the polarization of the voltage. So usually we use something like this green line because this green line actually matches the signal that would be generated for a standard AC generator with one loop. And basically what happens here is that electrons are going to be flowing in one direction initially, and then at some point they reverse directions and flow the other way, and then they reverse directions again, and so on. And as was mentioned earlier, it's easier to generate AC than DC, and that is again because this signal requires one loop on your generator, and that loop is basically in contact with a pair of single ring commutators. So both wires make a connection with a single complete all the way around 360-degree commutator, whereas in a DC signal you have to use split ring commutators, and in fact if you want to get even this signal, to say nothing of this one, you need to have many loops within your generator. So let's compare the two a little more. So far we have assumed a constant delta V for the DC voltage. In a similar manner, what we're going to assume is a particular form of the AC voltage, which will be basically sinusoidal. For what it's worth, this also implies that we have some equivalent to the delta V being constant, as we'll see shortly. In particular, the maximum potential difference is constant if you just have a simple sine wave. And as we will find, there is also an average potential difference, which will be also constant over many waves. So let's consider AC circuits with resistors, and this may be a bit of review. A resistor placed in an AC circuit might be drawn like this. So here's your AC source, here is your resistor. Your voltage alternates like a sine wave. So V equals V max sine omega t. Omega is the angular frequency of this sine wave. V max is the maximum voltage. Some sources like to label it as V naught for initial voltage. The current is given by Ohm's law, so that means V equals IR. Therefore, you're basically taking everything here and dividing by the resistance R. So I is V over R, that's V max over R, sine of omega t. V max over R would be I max, so electric potential difference divided by resistance is current, so the maximum potential difference divided by the resistance gives you the maximum current. And so I max or I naught would be the peak current, and you'll see that V and I are in phase. That means that both are at a peak together, both are at their troughs together, both hit values of 0 together, etc. If you want to get the power in an ohmic resistor, and this is true whether you use AC or DC, you use power equals the current times the potential. And that can be, for an ohmic resistor, the current squared times the resistance. It can also be the potential difference squared divided by the resistance. But the important two for today's purposes are actually these two forms that I've listed. So the instantaneous power that you're getting through a resistor for an AC circuit would be I squared max times R times the sine squared of omega t. So this is the current, the maximum current squared, times the resistance times the sine squared of omega t. You can see that basically what I've done to get that is I've taken this equation, this is the equation for the current I of t, and I've squared all the terms in it, and then I've multiplied those terms by an R, which is placed kind of in the middle here because it's less awkward than placing it after the sine squared of omega t. In general, the power you can get by figuring out what the area under the current squared curve would be versus time, or therefore you can basically find an average. And if you do that over one cycle, what you find is that the current on average is 1/2 of the maximum current. This should be squared. So the average current squared is 1/2 of the maximum current squared. And hence the average power is given by the average current. And so you would use average power is the average current squared times the resistance. And we define this average of the current squared to be called the root mean squared current. So root mean squared current is the average of the square current. Therefore, if you want to calculate the power, you can use the root mean squared current, and that is the maximum current divided by the square root of 2. Similarly, you can get the root mean squared voltage by taking the maximum voltage and dividing by the square root of 2. And in fact, the average power will be the root mean squared current times the root mean squared voltage. So that would be 1/2 of the maximum voltage times the maximum current. At this point, I want to introduce a new concept called a phasor. And a phasor is basically a diagram which you can use to represent both current and voltage for any given element within a circuit. So this right here is actually showing what the phasor might look like for a resistor in an AC circuit. For one thing, here is the current and the potential drop across that resistor within the circuit. There is basically a single resistor and a single AC voltage source. So this more purple colored curve is for the current, the more red colored curve is for the voltage. They are both sine waves, they are both in phase. The phasor basically says at some time t, what is the value of these two entities, the current and the voltage. And what it is that the length of the phasor gives the maximum value of the thing that it's a phasor for. So this red one is the phasor for voltage, and the length of this red one represents the maximum possible voltage in this cycle. The actual projection of this onto the y-axis represents the actual voltage at that time. So this is like taking, in a sense, it's like taking a dot product between this phasor and something that is in the vertical direction, the unit vector in the y direction, for example. And the same thing is happening here with the current phasor. The projection of the current phasor gives the current at some time. And notice that the angle that it makes with this axis could be given by omega t. This is assuming that initially the voltage and the current are zero. So initially both of these point in the x direction and you'd have zero current, zero voltage. And the angle through which this rotates, theta, should be equal to the angular speed times the time. Remember that the angular speed is another word for angular frequency, and in any case it is a constant. It is basically the period of this cycle reciprocaled and then multiplied by 2 pi. So omega is 2 pi over big T, where big T is the period. So after some time t, this thing has rotated through some angle theta equals omega t. And so you can figure out what the projections are onto the y-axis and see just what is the value of both the voltage and the current. We'll return to this thing later when we look at what happens to both a capacitor and to an inductor in an AC circuit. For the resistor, the diagram is kind of almost uninteresting in that both point along the same direction because they are in phase. And so they both rotate together through the same angle theta equal omega t. So again, what a phasor is that it is a vector which has a length that is proportional to the maximum value of the variable which it's representing, be it the voltage or the current. This vector rotates in the counterclockwise direction with an angular speed omega. That means that the angle that it's passed through, just doing simple rotational kinematics for constant omega, would be theta equals omega times t. The projection of the phasor onto the vertical, that is the y-axis, gives you the actual value at time t of the variable in question. So the current or the potential difference across the resistor in this case. And what it ultimately does for us is help simplify the analysis of an AC circuit with multiple elements, in particular elements like a capacitor or an inductor, although I'm showing this right now for the resistor. We'll see for a capacitor and an inductor later. Before we get there, I wanted to work a few simple examples, a few short examples based on what we've done so far today. Our first question is, what is the RMS current and voltage drop for a 50 ohm resistor in an AC circuit drawing a maximum current of 15.4 milliamps? So this right here represents I max. This right here represents R. Remember that I RMS is equal to I max over square root 2. So we would have 0.0154 amps divided by the square root of 2. And so if you do that, you get 0.010889. So that would be maybe 0.0109 just amps. And so that would be 10.9 milliamps. And that is the IRMS, the root mean squared current. To get the voltage drop, basically you can use that V is equal to I times R, and so V max is equal to I max times R, and V RMS is equal to I RMS times R. So you could either do it this way and then divide by a square root of 2, or you could do it this way. Both should give you the same answer. Basically, if you if you multiply this guy by 50 ohms, what you end up getting is 0.5447 volts. So that is the RMS voltage for this resistor. So now we need to figure out what is the average power draw of this resistor. So here again are the RMS voltage and current. Remember that the average power is the root mean squared current times the root mean squared voltage. So we'd have 0.54447 volts times 0.01089 amps. And so what we end up getting is 0.005929 watts. So that is the average power drawn by this resistor. So what is the instantaneous power draw at 2.0 seconds after the above resistor has begun to draw the current, assuming that we have an F equals 60 Hertz AC power supply? Well, recall that omega is 2 pi times F. Recall that the instantaneous power P is the instantaneous current I times the instantaneous voltage V. Or we could use I squared R. So that would be I squared for the maximum current times R times the sine squared of omega t. Because the instantaneous current is I max times sine of omega t, and we're squaring that. So the instantaneous power here looks like we have, since we had a 15.4 milliamps for the maximum current, we'd have 0.0154 amps squared times 50 ohms times the sine squared of, so omega is 2 pi f, so we'd have 2 times pi times 60 inverse seconds times the time, which is 2.00 seconds. So we've got a few things to calculate here. However, our calculations simplify dramatically when we see that this is 2 times pi times a whole number times another whole number. And so that means that we're going to have ultimately some even number times pi, and we're taking the sine of that. So this whole thing ends up being 0, because the sine of any full integer multiple of pi, the sine of any integer multiple of pi should be 0. So the power instantaneously at 2.00 seconds is 0 watts. Last part of this example is to draw the phasor diagram for voltage and for current at this time. So after setting up our axes and writing these equations out, note that this right here is going to be 2 pi times 60 inverse seconds times 2 seconds. So again, you're going to get I equals 0, and for a similar reason, you're going to get that the voltage drop is V equals 0. So what we have to do at this point is to draw out the two phasors, and both of them are basically going to be just along the horizontal axis like this. And so both phasors will basically look the same. They look like this. You'd need to set up maybe a scale if you wanted to. So my scale basically says that this distance right here is equal to V max. So from here to here, that would represent V max, and then over here, that would represent I max, both of which we've determined previously. Recall that if you have a capacitor that is connected to a battery or other DC source, that what basically happens is that it's going to accumulate charge on the two plates of the capacitor. So for example, this plate will accumulate a positive charge plus Q. This plate accumulates a negative charge minus Q. And this is because the charges are all flowing in one particular direction from a DC source. What that ultimately does is at some point you've accumulated enough charge on these two plates that no further charges will flow, and so basically that means that there will be no further current flowing through a circuit with a capacitor. In fact, there is no charge in between these two plates, and therefore there is no current flowing between the two plates. If you change this, however, to an AC circuit, you get a slightly different result. And the reason why is because the polarization of your source is switching in time. And so maybe initially the polarization is as if you have a battery of a plus here and a minus here, and that will result in this plate having a net negative charge and this one having a net positive charge. Well, over time, this is either increasing or decreasing, and so that means that it is either pulling charges away or putting more charges on to the capacitor. And eventually it switches signs. So even if there was a positive charge here and a negative charge here, when it switches, all the positive charges are going to suddenly want to come here to this negative terminal. All the negative charges are going to want to suddenly come here to the positive terminal. And what this basically means is that you have a current that's actually flowing in this circuit with a capacitor for a sustained length of time. This is basically as a result of the polarization changing within the AC source. Not only changing, but also the magnitude changes. If you want to figure out what the voltage drop across the capacitor is, you first have to find the charge that's on the capacitor. And that charge will have an equation of the form Q is negative I max over omega cosine omega t. Omega is, again, the angular frequency of your current signal. So this is the form of the charge buildup on each of the two plates of the capacitor. You can use a trigonometric identity that says that the negative of cosine omega t is equal to the sine of omega t minus pi over 2. So basically you're replacing the minus cosine omega t here with a sine omega t minus pi over 2. And that gives you the total charge Q. This basically means that you are shifting with respect to a sine by pi over 2, which is a quarter of a cycle. So if you look over at this graph, here's the current and here's the voltage, and the voltage has shifted to the right by 1/4 cycle everywhere. So the maximum for the voltage is at 0 for the current, the minimum for the voltage is at 0 for the current, and then the minimums on the voltage are at maxes and mins of current. The voltage drop itself is given by Q over C, and that's why this is this way, because we basically taken this Q equals I max over omega times sine omega t minus pi over 2. We basically taken that function and divided by a constant, which is the capacitance. So the voltage drop as a function of time is given by this equation. V equals V max sine omega t minus pi over 2. And that is where the maximum voltage is given by the maximum current divided by the product of the angular frequency and the capacitor's capacitance. You can also see this nicely in the phasor drawing for the voltage and the current. You can see here that the voltage and the current make a right angle with respect to each other. That here the current is basically leading the voltage by 90 degrees because both of them are rotating counterclockwise. So the current is actually leading the voltage by 1/4 cycle or 90 degrees or pi over 2, whichever one of those you want to say. In my previous discussions of inductors, I didn't really do much with an inductor in a DC circuit. You'll notice that I talked about capacitors and resistors in DC circuits, but not really inductors. The reason why is that an inductor is not very exciting when put into a DC circuit. Oh, it does one thing, which is that if you first flip the circuit on or flip the circuit off, it can create a pretty powerful back current. But that is usually a temporary effect that eventually dies out, and once the back current has died out, which is usually on a very fast time frame for most typical inductors, then the inductor just acts like another piece of wire. The reason for that is that if you have a DC circuit, you do not really have a changing current, and so without that changing current, you don't get a changing magnetic field, and hence no changing magnetic field flux, and hence no induced current or EMF. However, if you place the inductor into an AC circuit, as in this diagram, something interesting does happen, because an AC circuit provides a changing current. In fact, a continuously changing current. So that means that by Faraday's law, you can be continuously inducing some sort of EMF in this inductor. That EMF is basically given by L delta I over delta T. And we're ignoring any signs for now. According to Kirchhoff's rule, you get a voltage drop across this inductor, which has to be equal to the voltage drop across your entire loop, the rest of the elements of your loop, I mean. And so basically what that ends up meaning is that V sub L is L delta I over delta T. The current itself, I, has the form I max sine of omega t. It turns out that you can therefore find an expression for this voltage drop, and that expression is basically that the voltage drop is the angular frequency of your signal times the inductance times the maximum current times the cosine of that angular frequency times time. So we can again use a trigonometric identity. This time the one that we use is that cosine of omega t, positive cosine of omega t, is sine of omega t plus pi over 2, rather than the previous one that we used, which is minus cosine omega t, is sine omega t minus pi over 2. So our cosine trigonometric identity, we convert the cosine into a sine by way of adding a phase of pi over 2 or 1/4 cycle. So that means that the voltage is given by Vmax sine omega t plus pi over 2, where Vmax, the maximum voltage drop across the inductor, is given by the maximum current times the angular frequency times the inductance. So what this means is that the voltage drop across an inductor actually leads the current through the inductor by a phase of 90 degrees. In the capacitor, the voltage drop was trailing the current through the capacitor by a phase of 90 degrees. In the inductor, it's now leading by 90 degrees. So here's the phasor diagram that shows that. Remember, everything rotates counterclockwise. So here's the current, here's the voltage. And this is basically 90 degrees counterclockwise. The voltage is 90 degrees counterclockwise from the current. That means it's leading the current by 90 degrees. We're assuming here one thing, which is that we have negligible resistance in the inductor. It gets a little more complex if we add some resistance, as we'll see shortly. What is worth noting here is that we can now define a new concept, which is called impedance. And what impedance is it is something that relates the peak current to the peak voltage drop. So the equation that defines impedance in general is that the maximum or peak voltage drop is equal to the maximum or peak current times the impedance. So if you have a resistor, then the impedance is just R, the resistance value, because at all times V equals IR if you have an ohmic resistor, and hence the maximum voltage is the maximum current times the resistance. In the case of the capacitor and the inductor, you actually also can get values for impedance. They are 1 over omega c for the capacitor. That's 1 divided by the angular frequency times the capacitance. And for an inductor, you get ZL, the impedance, inductive reactance, is the angular frequency times the inductance. And you can see that by going back and looking at those previous equations. For example, with the inductor, V is equal to Vmax sine omega t plus pi over 2, where Vmax is Imax omega L. So if Vmax is Imax times Z and Vmax is Imax times omega L, then then Z is omega L. That is what you're multiplying the maximum current by to get the maximum voltage. And worth noting here, there's sort of two extreme cases. One is the case where your angular frequency is 0, in which case you have basically a DC current. What would happen? Well, your capacitor would have an impedance of 1 over 0, which is effectively infinite. And so the impedance for this capacitor for a direct current circuit is basically infinite, and that's why you don't get any current flowing through. In the case of the inductor, if you have 0 angular frequency, the impedance is 0, and so the inductor basically acts just like any other wire in your circuit. In fact, this is assuming that there is no resistance, no internal resistance for this inductor. If there's some resistance for the inductor, then you have an additional term, for example, plus R. And so with 0 omega, you'd have whatever the internal resistance of the inductor is becomes the impedance. If you have, on the other hand, omega approaches infinity, meaning the angular frequency is very, very high, near infinite, then you'd have a very, very large number down here, which means that you'd have virtually 0 as your capacitive reactance. But you'd have a very, very large number here, which means that your impedance is also very, very large for the inductor. So an inductor pretty much does not allow any current if you have an infinite or an infinitely fast AC source. But it allows current very easily if you have no AC source, if it's just a DC source. And a capacitor reacts in exactly the opposite way. It allows no current if you have a DC source, but it allows current virtually unimpeded if you have a very, very high frequency source. Let us consider a few short examples now of what we've been discussing with capacitors and inductors placed into a AC circuit alone. first question is, what is the impedance of a 250 nanofarad capacitor? So here's the capacitance. When it is placed in an AC circuit of frequency f equals 60 cycles per second. Now recall that omega is 2 pi times f. The impedance for a capacitor, called the capacitive reactance, is given by 1 over omega times c. So that would be 1 divided by 2 pi times 60.0 per second times 250 nanofarads. So that's 2.50 times 10 to the negative 7 farads. So that is what is going to be our reactive capacitance. So the answer is that the capacitive reactance is about 10,610. So I guess this would be 10,600. And the units you can see are basically per farad per second, or seconds per farad. And a second per farad is actually equivalent to an ohm, so 10,600 ohms. Ohms would be the correct unit of impedance, regardless of what you use for impedance, but you can check this by recalling that this unit, farads, is the unit that goes with a capacitance, and the capacitance is the charge stored per unit voltage. So this implies that farads are equivalent to coulombs per volt. And note that therefore you would have 1 over farad is equal to volts per coulomb. And so basically you have seconds dot volts per coulomb, which looks like seconds per coulomb dot volts. This right here is the units that goes with current, and this right here is the unit that goes with voltage drop. And recall that resistance is number of voltage drops per unit current, and that is in ohms. So this is 10,600 ohms. All right, our second question is, we want to know what is the maximum current, I max, which is drawn by the above capacitor if the AC source has a maximum voltage, delta V max, of 120 volts. Well, recall that the impedance is given by the maximum voltage is, whatever the impedance is, times the maximum current. So if we want to figure out what the maximum current is, we need to divide the maximum voltage by the impedance. So we would use I max equals delta V max over Z. So that's 120 volts divided by 10,600 ohms. So if we do that, what we end up getting is a total current of about 11.3 milliamps. So I max is approximately 11.3 milliamps. Now we basically want to redo this example, but with an inductor instead of a capacitor. So what is the impedance of the inductor? Well, the impedance Z sub L is sometimes called the inductive reactance, and so that is given by omega times L. So we would have 2 pi times 60 inverse seconds times 1200 picohenries. So that would be 1200 times 10 to the minus 12 henries. So this gives us a total of about 4.5238 times 10 to the negative 7. And again, the units here should be ohms. And I will leave that as sort of an exercise for the viewer to derive that the units of this are in fact also ohms, but you can do it by a similar process to the one I just did for the capacitor. Alright, so what's the maximum current that's drawn by this inductor? Well, again, you can use that I max is equal to delta V max divided by the impedance. So this would be 120 volts divided by 4.523 times 10 to the minus 7 ohms. And so this maximum current draw, I max, is going to be approximately basically 265,258,238. So we'd call that 265,258,238. So we could say maybe 2.65 times 10 to the 8, and that is in amps. Seems like quite a bit of amps, and to be honest, yes, that is, but again, this is because we're assuming that this is an ideal inductor with no internal resistance and it's not connected to any other resistors, so we'd rather expect to see a very large current draw. The follow-up question is, what's the instantaneous current 1 second later? Well, the instantaneous current, sometimes I, or sometimes you could write I of t, is the maximum current times the sine of omega t. So basically that means that we plug in this number that we just got, the 2.6525 or whatever, times 10 to the 8 amps, and we multiply that by the sine of 2 pi times 60 hertz times 1 second later. And actually what we might want to do is note that we didn't have to have a plus pi over 2 or a minus pi over 2 in order to get the answer correct. And so it's easier, in fact, to convert this to just a cosine of all this, because we're basically shifting to the point at which we have our maximum current and calling that time 0. And so that goes with a cosine function rather than a sine function. And so if you look at all this, you'd have 1 second times 60, that's an even number, times 2 is 120, times pi, that's an even number. So this is an even number times pi. This whole entire cosine would be 1. And so the instantaneous current is in fact equal to the maximum current at that time, or 2.65 times 10 to the 8 amps. So that is, again, because we are through an even increment of these, and it's basically an integer increment of pi's cycles that we've gone through at this point in time. In other words, the frequency was 60 cycles per second. That means that after going through 1 second, we've just gone through 60 whole cycles, so we're back to wherever we started from. And so therefore we're back to the maximum current because that's where we're starting from. Now we're going to consider what happens when you place an inductor and a resistor in series together. And we'll start with, of all things, a DC signal. And I kind of said earlier that it's not super interesting what happens when you have a DC signal and an inductor, and that's true, except for in the moment when you switch from having the circuit off to having the circuit on, or from having the circuit open to circuit closed, or however you want to say it, when you connect or disconnect the battery from the circuit. So we consider a circuit diagram like this. There's a switch. When it's in the position 1, you have a battery in series with an inductor in series with a resistor. When it's in position 2, the battery is removed from the circuit and you just have a resistor and an inductor in series. So basically you're going to get something that looks like this when you first connect or disconnect the combination. If you place an inductor in series with a resistor and you'd put this into a circuit, then the result is, as long as you just have a simple DC circuit, it'll just act like a resistor. So as if you'd connected a battery to just the resistor. However, if you have a switch where you switch the battery on or off, you do actually get some interesting result. And I kind of alluded to that earlier. Now I want to describe it a little bit. Basically what happens is, in the moment when you switch the battery on or switch the battery off, you change what the magnetic field is. And by doing that, you change the magnetic flux and thus induce some sort of an EMF from the inductor. So you get some sort of back current. And ultimately, you can measure what the current through the resistor is. And it actually has solutions that are kind of sort of similar to what happens when you either charge or discharge a capacitor, charge a capacitor or discharge a capacitor through a resistor. Basically, the equations are the same, save that instead of using charge as a function of time, charge equals the initial charge, or the maximum charge, times 1 minus e to the negative t over tau, you have current. And current is voltage drop over resistance. So it's whatever the final voltage drop, or the maximum voltage drop, I should say, across the resistor, times 1 minus e to the negative t over tau, where in this case tau is L over R rather than the RC time constant, which was tau equals RC. So here tau is L over R. And when you are disconnecting a battery, you basically get a decay like this. I equals V naught over R e to the negative t over tau LR. In this case, it probably actually is better to use V naught than just V max. Here you'd get sort of like a V max if you had a DC current. V naught actually in some sense makes more sense, simply because you could have had an AC source connected initially and you've disconnected the the AC source. And this right here still would describe what the current through that resistor is, provided that you understand V naught to represent whatever voltage drop you had in the moment that you flipped the switch and basically disconnected the AC source. So you basically get an exponential, a decaying exponential rise and an exponential decay. And in both of those cases, what that basically means is that you have an asymptote that you're approaching. In the case of charging the battery, the asymptote, in the case of connecting the battery, the asymptote is at the maximum current that you'd have, which is basically equal to the voltage drop from the battery divided by the resistance. In the case of the decay, it's asymptotic to 0. So after much time, you're very much approaching 0 current, but you may or may not actually reach 0 current. All right, let's consider what happens if you have a charged capacitor that's connected in series with an inductor. Well, the capacitor in this case is going to discharge through the inductor, and that's going to produce basically a changing current and hence a flux in the magnetic field. So, hence a changing flux in the magnetic field, that is. So, by Faraday's law, that means you're going to get an induced EMF. Now notice there were no batteries connected to this. All we've done is closed the circuit so that this thing begins discharging, and what has happened is we've induced some EMF. Basically what that does is the capacitor eventually finishes discharging, and at that point you have a very, very large induced EMF for the inductor, and so then current is flowing thanks to that EMF. Basically, you start recharging the capacitor, possibly on the opposite plates, and so you end up getting that the charge on the capacitor follows a sinusoidal pattern. In fact, it follows the same pattern that a simple harmonic oscillator would have followed. If you think of the charge on each plate of the capacitor as being equivalent to, for example, the displacement of a mass on the end of a spring. This is the same exact equation that you would get for that, but we replaced the displacement x with the charge q. And similarly, that means that the current I of t is negative I max sine omega t plus some phase. This is plus some phase. Probably the phase is 0 for our purposes. This has the same equation form as the velocity of the mass on the end of a spring would have had. So this LC circuit actually behaves very much like a simple harmonic oscillator, but we've replaced displacement and velocity with charge on the capacitor and current flowing in the circuit. All of this, again, is just a consequence of Faraday's law. The other thing is that the frequency at which this oscillation occurs is given by 1 divided by the square root of the product of the inductance and capacitance. So that means that this resonant frequency is also obtained from properties of the stuff that are oscillating, much like the resonance frequency of the harmonic oscillator was obtained from the mass and the spring constant. It has a slightly different form, however, than taking square root of k over m. In this case, it's 1 over square root LC. You'll also notice that the phase is 90 degrees difference between the charge and the current, which is in fact the same thing that we had when we looked at the phase difference between the displacement and the velocity for a simple harmonic oscillator. Basically, the maximum velocity occurs for the minimum displacement from equilibrium and vice versa. Here, the maximum current basically occurs when the minimum amount of charge is stored on the capacitor. And physically, you can interpret that as meaning that basically the current is being caused solely by the charges in the capacitor moving, and when all of those charges are off the capacitor, you have the most amount of current moving through the circuit. So now we look at the energy that's being stored in the LC oscillator. So again, this is a simple LC oscillator. We assume no resistance. If you had resistance, basically it would mean that over time power is being dissipated by the resistor, and so this would be dying out. Without the resistor, or without the resistance being added, you just have a simple LC oscillator. We can make a simple assumption that says that the total energy stored must be equal to the initial energy stored on the capacitor. That should make sense because eventually there's no charge on the capacitor, and if there's no resistor to dissipate that energy, then that energy must be somewhere else in the system. Namely, it might be in, for example, the magnetic field within the inductor. So the initial energy stored on the capacitor is 1/2 of the charge squared over the capacitance. You can review the notes on capacitors if you've forgotten that equation. The total energy within the system has to be the energy stored by the capacitor plus the energy stored by the inductor, which is basically the energy stored as potential energy in the electric field plus energy stored in the potential energy of the magnetic field. So the charge on the capacitor is actually given by whatever the initial charge was. It could be Q naught or Q max is the same thing. That squared times the cosine squared of omega t plus this phase. So we take the phase usually to be 0. Q max is Q naught if you have no damping or driving, meaning if there's no resistance in this and no electrical power sources like an AC source or an additional battery, anything like that, then these two should be equal. So this equation basically came from, therefore, just taking the literal equation that we got earlier for the charge on the capacitor and squaring it, because that's what we're supposed to do to get the potential energy, and then dividing by 1/2 and dividing by C. So that's the over 2C part. That's how much is being stored by the capacitor at any given time. So for the inductor, you have that the energy is 1/2 of the inductance times the current squared. So that ends up looking something like this by the time all is said and done. And remember, omega squared is 1 over LC. So we could take this omega squared and substitute a 1 over LC for it. So that would cancel 1L and you'd be left with an L on the bottom. And you'd have, you'd cancel the L's from top and bottom and you'd have a C left on the bottom. So that gives you Q squared max times 2C times sine squared of omega t plus phi naught. So we have a cosine squared times Q max squared over 2C, and we have a sine squared times Q max over 2C. So that means we have a sine squared plus a cosine squared that equals 1. So that means that the total energy stored by this entire system is Q squared max over 2C, which is exactly what we would have expected. It's basically what the initial energy was stored on just the capacitor. So let's look at a few last examples. Our first example, we have an 800 nanohenry inductor connected in series to a 2 kilo ohm resistor, and then that's connected to a 9-volt battery. So maybe we should start by drawing a diagram of this circuit. Basically, you have your 9-volt battery, you have a resistor somewhere, and then you have an inductor somewhere in the circuit. These guys are all in series, and then there's something like a switch, and this thing switches so that it is closed. This guy, R equals 2.0 kilo ohms, L equals 8.00 times 10 to the negative 7 henries, and the voltage for the battery, delta V naught, is 9.00 volts. So we close the switch, and we want to know what is the voltage drop across the resistor after 1 picosecond. So this is time t equals 1.00 times 10 to the minus 12 seconds. So recall that the voltage drop, we're looking for basically delta V sub R. The voltage drop delta V sub R is I times R, and I is I of t, so basically we have V naught, or delta V naught, over R times 1 minus e to the negative t over tau RL, and then that's times R. So you can see that these two resistances should cancel. And recall that this guy right here, this time constant, is the inductance over the resistance. So that means that we can basically say that the voltage drop at this time is the maximum voltage drop possible, the 9.00 volts, times 1 minus e to the negative 1.00 times 10 to the minus 12 seconds times 2 by 10 to the 3 ohms divided by 8 times 10 to the minus 7 henries. So what that gives us is basically, bearing in mind that everything in this exponential ends up being basically 2.5 times 10 to the minus 3, that if you take e to that, what you end up getting is 0.997503 or some such thing. So if you subtract that from 1, what you end up getting is that all of this is 0.0024968 or whatever. And that is being multiplied by the 9 volts. So if you multiply that by your 9 volts, you end up getting that the voltage drop at this time is approximately 0.02247. So 0.225 volts. So that's what our voltage drop is going to be after 1 picosecond. Now notice that that's somewhat different than what we would have assumed in the ideal case of a circuit that has no inductor. This thing closes, and instantly what you end up having is 9 volts. And so at 1 picosecond you would have had 9 volts. But remember that this entire circuit is itself a sort of inductor. So that means basically that we'll have somewhat less than 9 volts at this 1 picosecond time. At what time will this resistor have a voltage drop of delta V equals 8.1 volts? Well, delta V is again delta V naught times 1 minus e to the negative t over tau. And so basically we can say that delta V minus delta V naught is negative e to the negative t over tau. So therefore we can sort of take a logarithm of both sides. Alternatively, we could actually divide everything by this delta V naught. I left off a delta V naught over here somehow. So we need to divide everything by a delta V naught to make this work. So that would be like this. So you have delta V over V naught minus 1 is equal to negative e to the negative t over tau LR. So if you want to get rid of this exponential, you take a natural log of both sides. So negative t over tau LR would basically be equal to the natural log of of 1 minus delta V over delta V naught. And now we can plug some numbers in. So you get something like this. Plugging some numbers in, and what you end up getting is that t is 9.210 times 10 to the negative 10 seconds. So that would be 921 picoseconds, 921 times as long as the amount of time that we solved for the voltage of in the first part. Finally, we ask what's the resonance frequency for a circuit containing a capacitor that is a 0.1 millifarad capacitor and an inductor that is a 1200 nanohenry inductor. So basically you have this circuit right here. There's a capacitor, there is an inductor, and we want omega, which is 1 over square root L times C. So that is 1 over the square root of, this is 1.00 times 10 to the minus 4 farads. And then this other guy is 1.200 times 10 to the minus 6 henries. So that gives us basically 1 over the square root of 1.2 times 10 to the minus 10. So that gives us a frequency, an angular frequency that is, of about 9.1287. So maybe 9.13 times 10 to the fourth power in inverse seconds. So 91,287 inverse seconds, or radians per second, is what our angular frequency is. That may sound like a big number, by the way, but that's actually a relatively low frequency circuit, in large part because this is a pretty big capacitor. If you think about what would be the resonance frequency of, let's say, a circuit that wanted to operate at a radio frequency. Radio frequency, maybe you listen to the FM radio, that's usually 101 megahertz. So that's many times this resonance frequency. That is, however, a subject for a future lecture. There are quite a few new terms that were introduced in this. Some actually are old terms in the sense that I did mention them in a previous lecture set, but only in passing. Actually, most of the stuff on this first page is from an old lecture, but there's 2 more pages worth of these summaries. So we start off with the form of the voltage and the current that go with a standard AC signal. This is the kind of signal that is going to be produced by an AC generator. Omega represents the frequency of the signal. It also would actually represent the angular frequency at which the generator is rotating. The instantaneous power for that is obtained by using the root mean squared current or the root mean squared voltage, or both, where the root mean squared current is the maximum current over the square root of 2, the root mean squared voltage is the maximum voltage over the square root of 2. And so that is just AC in general. Now we turn to specific components of AC circuits. For starters, the phasor, which is a vector which has a length proportional to the maximum value of the variable which it's trying to represent, and whose projection onto the vertical axis represents the instantaneous value of that variable. They're useful for analyzing different elements within an AC circuit. The voltage drop across a capacitor in an AC circuit tends to trail the current through that capacitor by 90 degrees. And that can be easily shown by looking at the phasor for the capacitor in an AC circuit, which was figure 9.2.8 in this lecture. Here's the voltage, here is the current. It rotates counterclockwise, so the voltage is trailing the current by 90 degrees, and here of course is the voltage and here is the current. The maximum voltage in any case is the maximum current divided by the angular frequency times the capacitance. This 1 over omega c term is in fact the capacitive reactance, which is the impedance for a capacitor. If you look at a instead of a capacitor, if you look at an inductor, then you get that the voltage drop in the circuit will lead by 90 degrees. So again, it's a quarter of a cycle out of phase. And again, if you look at the phasor, you can see that the current is trailing the voltage for our inductor. And again, by 90 degrees or 1/4 cycle, because once again, we go in the counterclockwise direction. The impedance is another new term that was introduced. I already talked about it in terms of the capacitive reactance. There's also an inductive reactance that goes with inductors. And it relates the maximum voltage to the maximum current. So Vmax equals Z times Imax. The maximum voltage for an inductor is the maximum current times omega, the angular frequency, times L, the inductance. So the inductive reactance is omega times L, and that is the impedance that is given by an inductor. Of course, for a resistor, the impedance is just equal to the value of the resistance. If you have an LR series circuit, then it's going to basically, if you put it in series with a battery and then either connect or disconnect the battery, you will not instantly lose or gain current, but instead will have an exponential rise or decay when you connect or disconnect the battery. And in both cases, the relevant time parameter is given by the inductance divided by the resistance. This has a similar equation, similar form to the equation, I should say, as the charge stored on a capacitor when charging a capacitor through a resistor. The difference being that instead of being concerned about what's the current, we're usually concerned by what's the charge. So it would be charge equals initial charge times all this stuff, where this time parameter is replaced by the RC time constant, and similarly here. So for the inductor, it's current equals the voltage drop of the battery divided by the resistance times 1 minus e to the negative t over L over R, and I equals the voltage drop of the battery over R times e to the negative t over L over R when you disconnect the battery. Note that you can also get the voltage drop across the resistor by then multiplying everything by R. If you have an LC circuit instead of an LR circuit, then what you have is a sort of simple harmonic oscillator. You have the circuit equivalent to a simple harmonic oscillator, where charge takes the place of displacement and current takes the place of velocity. And again, the current is 90 degrees out of phase with the charge. That makes sense again because basically you can treat it as if all the charge is on the capacitor itself, and that's all the charge that can make up the current. So when there's zero charge on the capacitor, all the charge is in motion, and therefore you have a maximum current. And when all the charge is on the capacitor, there is zero current left in the circuit to move, and hence you have zero current. Similarly, you can determine how much energy is stored in this LC circuit by using that the energy is stored between the electric field and the magnetic field. The total potential energy is the maximum amount of charge stored on the capacitor divided by 2 times the capacitance, total charge squared. And both the electric and magnetic fields will have energies that go like the cosine or the sine squared of the frequency at which this oscillation is occurring. And the frequency at which the oscillation occurs is 1 divided by the square root of the inductance times the capacitance. So that's the resonance frequency for this circuit. I believe that this brings us to the end of this lecture part, and indeed of this entire lecture set. So thanks for having watched this. We have talked about quite a bit in between discussing inductors and then discussing inductance and then discussing AC circuits. So I hope that you are able to kind of keep up with all that. It was kind of a faster pace than many of my lectures in that there were a lot of things introduced here, but to some extent a lot of those things are sort of the same thing in different forms over and over again. So hopefully you're able to make those connections between old concepts and new ones. And in the meantime, I hope that you enjoyed this lecture. And next time we're going to look at Maxwell's equations, Maxwell's predictions, and of course we're going to look at electromagnetic plane waves. So stay tuned for that. Until then, thanks for watching and farewell.